Hey everyone, welcome to this explainer. Today we're tackling one of the most significant tensions in modern computer science. On one hand, we've got the immense, literally world-changing analytical power of artificial intelligence. But on the other hand, we have its incredibly frustrating lack of transparency. We build these massive, brilliant models, yet when they make a decision, we often have absolutely no idea how they arrived at it. It's what we call the black box dilemma. And today, we're going to explore a fascinating research breakthrough that aims to finally crack that box wide open.
Here's our roadmap for today. We're going to start with the AI black box problem and the accuracy versus transparency trade-off. Then, we'll meet the RRL algorithm, break down how gradient grafting works, test the model against real data, and wrap up with the future of transparent AI. Let's get into it.
Section 1. The AI black box problem. High stakes, zero visibility.
We're dropping machine learning models into some really high-stakes domains right now. Medicine, finance, politics. In these areas, we absolutely have to know how a decision is made, right? High stakes demand high visibility. But, ironically, with our most powerful models, we get almost zero. So, imagine a world where AI doesn't just output a yes or no, but actually hands you a readable list of logical rules explaining exactly why it made its choice. This is the holy grail of machine learning, models that earn our trust by being completely transparent.
Moving to Section 2, accuracy versus transparency, the ultimate trade-off.
So why can't AI just show its work? Well, it boils down to this massively frustrating trade-off. On one side of the ring, you have deep neural networks, or DNNs. They scale beautifully to massive data sets, but they act as complete, unreadable black boxes. On the other side, you've got traditional rule-based models like decision trees. Super transparent, really expressive, but they just choke on massive complex data. Since they rely on discrete parameters, optimizing them with modern continuous math, like gradient descent, is notoriously tricky. So we've been stuck having to choose. Do you want it to be accurate, or do you want to understand it?
All right, Section 3, meet the RRL algorithm, the best of both worlds. To tackle this, researchers over at Tsinghua University and East China Normal University asked a pretty bold question. How can we scale up rule-based models without losing that sweet interpretability? And their answer is RRL, or the Rule-Based Representation Learner. This is a real aha moment for sure. RRL is a novel classifier that basically gives us the best of both worlds. It automatically learns highly interpretable, non-fuzzy logical rules, but, and here's the kicker, it scales like a neural network by searching for discrete solutions inside a continuous, smooth mathematical space during training.
So how exactly does it pull this off? First, it uses hierarchical logical layers for automatic feature discretization. It's also super flexible, learning rules in both conjunctive, and disjunctive, or forms simultaneously. But the absolute game changer here is the math. Usually, simulating logic mathematically makes your numbers multiply and shrink to zero, the classic dreaded vanishing gradient problem. Well, the researchers actually built improved logical activation functions that act like a mathematical safety net, dodging that problem entirely. This lets RRL handle thousands of features without breaking a sweat, all while letting you dial in the exact trade-off between accuracy and model complexity. Section 4. How gradient grafting works, the botanical breakthrough. Now, having a clever architecture is fantastic, but actually training discrete models, that's a whole different beast. The big technical roadblock here is that standard optimization needs smooth, continuous data to calculate gradients and minimize errors. Logical rules, though, are rigid. They're discrete steps. That means their gradients usually offer literally zero useful information. So you're left with this puzzle. How on earth do you train discrete, rigid rules inside a continuous, smooth space? They cracked this by borrowing an analogy straight from botany called gradient grafting. Think of grafting a plant. You take the strong roots of one plant, the rootstock, and attach the flowering stem of another, the scion. In RRL, the rootstock is the gradient of the continuous differentiable model's output. It gives you that smooth foundation that gradient descent desperately needs. Then, the scion is the gradient of the loss function regarding the discrete rules we actually want to train. By grafting these together during backpropagation, the algorithm directly updates the discrete parameters using the smooth gradient info. It's an incredibly elegant solution to a massive mathematical headache. And honestly, just a really cool use of biology and computer science. Which brings us to Section 5, testing the RRL model. The proof is in the data. Because let's face it, brilliant math doesn't mean much if it flops in reality, right? We need the real-world proof. Looking at the F1 scores across these datasets, RRL completely dominates traditional interpretable models like CART across the board. But what's truly mind-blowing here is that RRL actually rivals and sometimes beats complex black box ensemble models like Random Forest. I mean, on the Banknote and Connect 4 datasets, RRL's performance is phenomenal. It definitively proves you don't necessarily have to sacrifice high accuracy to get transparency.
And this is what actual transparency looks like in action. We're looking at real output from an RRL trained on a bank marketing dataset, trying to predict if a client will subscribe to a term deposit. Instead of some unreadable mathematical soup, it literally hands us plain logic. Take that third rule, for example. It basically says, if the person's age is over 36, and their balance is below 7016, and they're married, and the previous campaign was a success, boom, they are highly likely to subscribe. It's so incredibly easy for a human marketing team to read this, verify if the logic makes sense, and actually base real business strategies on it.
Finally, Section 6, the future of transparent AI, earning human trust. This brings us right back to those high-stakes domains we talked about at the start, where AI transparency isn't just a nice-to-have luxury, it's an absolute requirement. The true power of the rule-based representation learner is that it literally gives practitioners a dial. You can adjust the regularization during training to trade off between a super accurate model with slightly more complex rules or a highly simplified model that literally anyone could instantly read. This connects right back to our fundamental human need for trust. It's an AI that doesn't just blurt out an answer, it steps right up to the whiteboard and shows you its work. By proving that we can actually apply neural network-level scalability to transparent logic-based models, RRL is breaking that black box wide open. Which leaves us with a pretty profound question as these models continue to scale up. As algorithms take on more and more critical roles in our society, will we reach a point where models that refuse to explain themselves are simply no longer tolerated? Will transparent AI become the new standard for earning human trust? It's a fascinating thought to leave you with. Thanks for joining me on this explainer. And remember to keep questioning the algorithms around you.